All right. Okay. Oh, whoa, we got David Engelhardt in the house. We got Steve. Oh, wow, we got, all right. Also, conductor heat. Oh, here we go. Welcome, everybody. So we're going to talk motors, and we're going to talk ampacity, all that good stuff, and all that jazz. And we got Steve. The conductor heat sinks the heat away from the terminals. Yes, about 60 we can splice. You're absolutely right, Steve. And David Engelhardt in the house, they're already going at it. 110.14c is the equipment, not just the terminals that connect to the equipment. Oh, very good point, David. That is a very good point, because the temperaturized tests in a piece of equipment don't just look at one thing. They look at multiple measurements of temperature in the assembly. So it's not just, and the reason I say that, oh yeah, this is a good discussion. A while ago, I had an application where we had a product line that wanted to add 90-degree lugs on the equipment. And I asked, why are we doing this? Why is this project going on? And their comment was, well, we want to be able to use 90-degree C insulated conductors. And the right answer to that was, just putting a 90-degree C lug in there doesn't mean that now you can use a 90-degree C insulated conductor at its 90-degree C ampacity, because you can always use a 90-degree C insulated conductor on any lug. You just can't use it. You can't pull more current through it than what's in that temperature rating in that column. So it's not just about the lug. That lug can say 90-degree C, but if the overall equipment, the assembly, says it's a 75-degree C piece of equipment, then it's 75 is your limiting factor. So that is a very good point. Yes, so yes, I would agree with you. The only, I'll tell you where I would somewhat, I think in general you're right, David, but I remember Schneider released a product released like a box that had a terminal block in it, and then it would let you transition, and it was 90-degree C rated, but the equipment would have to be 90-degree C. It's not just the lug. So even if I put a terminal block inside of a piece of equipment and said that terminal block is 90-degree C, if I want to list that, then I would have to get it evaluated as an assembly, because the enclosure size, all that jazz makes a difference. I just want to make sure I put this on stun, because I don't need my phone ringing. All right. So very good points. Very good points. Steve says, good afternoon. At the end of yesterday, you said you were looking for help on understanding, was the 75-degree column because the terminals, there's almost none that are... Okay. I will explain what I meant yesterday here in a second, Steve. And we got Ahmed. Okay, so Alan Bernstein. And you know what, Alan? We never connected. We're going to do that. Sorry about that, buddy. All right, so here is my, oh man, we got another comment. Hold on, Steve. I've never seen 90-degree C rated equipment terminations for field wiring, but I think the NEC provides for it when it says unless marked otherwise. Maybe it's something special. So I'm going to do something I don't do. There was a product that Square D had, and I remember seeing it at an IEI meeting. It was just it was a termination in a box, and it was listed for 90-degree C. So you can come off of 75-degree C equipment, go to this box that basically transitioned you from 75 to 90, and you can have one box on either end of that feeder. And then you could put a smaller conductor there, and that really, it would have to, the only way for you to justify that would be the savings in size of the conductor based upon the length of the run. It would have to be a long run, large conductor, all that good stuff. But Steve, I agree with you in general, and the only reason I would not typically advertise a Square D product, but I do remember seeing them having that solution on the market. And we got, thank you, Alan, splice boxes with 90-degree C splicers at each end. Yeah, could be appropriate for before terminating. Yes, and that's the splice box. That's the one that I have seen. That there was one manufacturer that I will no longer say who they are, but that they'd had that solution. I don't know how many of these they sell, but hey, it's a solution. So I'll tell you why at the end of the discussion yesterday. Yesterday was Tuesday. I'll tell you why. If you look at, I gotta close some of these windows. Man, oh day, I got so many windows. And oh, by the way, NFPA Link now has the 2026 code. So that's a good thing. I gotta close my travel, my Concur, my Marriott, my 1 and 2 family, my speed test. All right, so here we go. So if I go to chapter 4, and I know somebody complained about me spending a lot of time on this on one of my videos, and they said, boy, you spent a lot of time talking about 75 versus 90, but this is a very important piece of the puzzle. In 430.22, is it? 430? Yes, motor circuit conductors. So in 430.22, it says conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the motor full load current rating. Now, when you say ampacity of the conductor, I'm thinking conditions of use. When you think about the termination, 110.14 gives me a limit of the amount of current that can pass through that termination based upon the size of the conductor because of the reasons that were stated earlier. Steve said and David said it's that conductor, the size of the conductor, the copper that's there helps with dissipating the heat, okay? And I gotta make sure that I don't raise that terminal above 75 degrees C. So if I look at chapter 3, if I go to 310.16, and I go to 310.16, now, what I'm telling you, keep in mind, if you're going to take a test, what we're talking about, if you do what I'm saying that the code actually permits as opposed to what we do in industry, you'll probably fail an exam because the exam is based upon, I believe the exams are based upon selecting that conductor at 75 degrees C. I've watched many videos so far. Every single one of them all do the same thing. And what I'm questioning is why, right? So, and I'll give you an example. Let me open up my spreadsheet. I have a spreadsheet which I've showed everybody. Camera A, monitor right. There we go. I've showed this spreadsheet a few times. You know me, I like spreadsheets. So what I did was I have my horsepower, I have the marked full load amps on the motor, I've got the voltage of the motor, the service factor. Right now this whole spreadsheet works off of a 1.15 service factor. If you did anything different, it ain't gonna work. This is the full load current that's based upon the table, and the table in the National Electrical Code. Remember what we said, whenever I'm doing a circuit, I am going to build an infrastructure for my motor circuit such that if I have to swap out that 5 horsepower motor for another 5 horsepower motor and that full load marked full load amps is 15 instead of 14 or 14.8 or something like that, it's not going to exceed 16.7. So I have an infrastructure based upon the table of 16.7, and I can tweak my overloads to get this motor to run and not have a problem with having to change my infrastructure. What I did was, what we do for sizing the conductor is we take 1.25 times the full load current, which is out of the table, not the motor nameplate. So I have 1.25 times 16.7 is 20.9. Now I have to make a decision. When I go to select my conductor that has the right ampacity, if I have a 90 C insulated conductor, what I would typically do is I would go to the 90 C column, because this is the ampacity of this conductor based upon conditions of use. So if I read the code verbatim, it says that in this step, that the conductor has to have an ampacity no less than 1.25 times this value, and that is 20.9. So if I go to this column and I find 20.9, my first one is a number 14. Now, and everybody teaches it this way, a different way than going to the 90 C. They'll tell you the motor is 75 C. That's your driving factor. So you go to the 75 C column and you do the same deal. Now a number 14 doesn't work. Now you have to go to a number 12. So I'm sitting there saying, I would have picked, based upon that language, I would have picked a number 14. But everybody else goes to a number 12. That's not a bad thing to supply a larger conductor. So let's go with it, right? So then what I did was, in here, I said, all right, and we're going to do this one right here. So let me highlight it yeller. So I have based upon the 90 C column, I pick a number 14, which has a 25 amp ampacity based upon the conditions of use. And that is 3 current carrying conductors in a raceway, 86 Fahrenheit ambient. Now, if I have a hotter ambient, I may have to go to a larger overcurrent conductor, because the ampacity of the conductor has to be greater than 20.9. Now, my 90 C column is 25, but my 75 C column is 20, which means I can't, when I land this conductor, when I land this 14 gauge conductor on a terminal and in equipment that's rated for 75, I can't exceed 20 amps, because if I exceed 20 amps, I raise the temperature of that termination above 75 C, and that would be ungood. Over time, it would be extremely ungood, right? Immediately, I'm not going to see a difference. I'm going to elevate the temperature, and I'm going to operate that equipment at a temperature, possibly, if I exceed 20 amps, if I don't protect it at 20 amps, if I protect this, since the ampacity is 25, Article 240 says I can go to the next larger, and 240.4 says, or 240.6 is my ampacity, standard ampere ratings. So if I go to 240.6, there's a table. Right? So if I look at the table, if I said I had a 25 amp conductor, I have a 25 amp breaker. So I would have to use a 25 amp breaker. And if I used a 25 amp breaker, that means I could have 20 amps flowing through the circuit. Actually, if it's a 25 amp breaker, what's 25? 25 times 0.8 is 20 amps. So I can't put more than 20 amps through that breaker anyway, because it's 80%, right? So that's not a bad thing. That's actually a good thing, right? So I would have to protect it at 20 amps anyway if I had a 25 amp breaker. So my overload can't exceed 20 amps. All right, so let's go back to 430. Actually, let's go back to my spreadsheet. Now, if I went off the 75 C column, I would pick a 12 gauge. My 90 C, my ampacity is now 30 amps. And now my 75 degree C column says I can have 5 more amps. When I increase the size from a 14 to a 12, I can put 5 more amps of current through that termination. Then I won't exceed the temperature rating of that equipment or the termination, however you want to look at it. All right, so now I can pull a little bit more current. So then what I did was I said, all right, so what's the overload? The overload, if I go to the code and I go to the overload section in 430, overload is in part 3, I think. Motor branch circuit and overload protection, continuous duty motors. It says that I have to have, for a separate overload device, motors marked with a service factor of 1.15. What I love about this is it says the device shall be selected to trip or shall be rated at no more than 125%. So if I have a 30 amp breaker, or if I go back to my example, if I take, and I can do this off of the nameplate value, I take 1.25 times the full load amps that's marked on the motor, which is 14. 1.25 times 14 is 17.5. I can't go to the next larger size. I can't say, well, I don't have an overload at 17.5, so I'm going to put an 18 or a 9 or whatever the next one is. I don't have that. My overload protection cannot exceed 17.5. And when I compare 17.5 to the 75 degree C column of my 12 gauge conductor, it's 25 amps. My 17.5 overload will protect a 12 gauge conductor at its 75 degree C for the equipment. That 17.5 overload will also protect my 14 gauge because it's less than 20 amps. So then I said, well, so far I can use either the 90 degree C method and have a smaller conductor on this motor, where everybody else teaches this, and probably the tests are driven off of using the 75 degree C column. Again, I still don't understand why you would do that, but I'm okay with that. And I think the reason is because they're saying, well, 110.14. But 110.14 just tells me I need to protect it. I can't draw more than 20 amps on a number 14 or 25 amps on a number 12 through the equipment that is rated 75 degrees C, even though the insulation of that conductor is 90. So then I said, if you look at the code, if you look at Article 430, and you go down, if you're in 430.32 for continuous duty motors, you get through A, you get through B, selection of overcurrent devices. Here we go. Where the sensing element or setting or sizing of the overload device selected in accordance with 430.32A1 and B1 is not sufficient to start the motor to carry the load, higher size sensing elements or incremental settings or sizing shall be permitted to be used. And they tell you for a service factor of 1.5 or greater, I can go up to 140%. So now that tells me that if I installed this motor, 5 horsepower motor, I put a number 14 gauge on there, I set the overload at 17.5, which is 125%, and it trips, I am permitted, based upon first level subdivision C, when I size this, and it's not sufficient to start the motor to carry the load, I can go up to 104%, 140%. That's another, what? That's another 15% on top of the 125. So what I did was I said, let's do that. 140% is 19.6. 19.6 is less than the 25 amps for a 12 gauge. It's also less than the 75 degree C column for a 14 gauge. So even if I adjust it to 140%, For this motor, I'm protecting the termination based on 110.14. I'm obviously protecting the conductor well below its ampacity because 240.4 would let me go to a larger size breaker on this 14 gauge, right? Well, not really, because it's a small conductor and I don't have to follow the small conductor rules. That's the other revelation that you have with Article 430. I don't have to follow the small conductor rules. But if this is a branch circuit, I would be mandated by 240 to put, because it's a small conductor, a 20 amp breaker on that, which aligns, is that a 20 amp? No, that's a 15 amp because it'll line up with a 14. If I look at the 60° C column on a 14, there's a 14. Yeah, 60° C column is 15 amps. A 12 is 20, right? So we line the overcurrent protection up with the 60° C column because of what? 110.14. It's not because the conductor can't handle it. That conductor can handle 25 amps all day and all night. The reason we go to 60° C is because of the termination. And I have to protect it at that value so I don't exceed it. And if I'm on a 14 amps, if I'm on a 15 amp or a 20 amp circuit, I'm probably hitting wiring devices and other equipment that is rated 60°. Most of that equipment is 60° C terminations. So they make you protect it at its 60°, and they treat it specially for both short circuit and because they don't want you to put a larger breaker. I don't want to put a 20 amp breaker on a 14. Why? Because the equipment can only handle 15 because of the limitation of the 110.14, the limitation of how much current can be drawn through that termination with that size conductor. So, all right, so now what I did was I said, let's check it out. Let's check out the 90° C value and the 75° C value. So then what I did was I said, I went online and I just searched a lot of different motors. All of these line items are different motors that I found online, and a lot of them were for sale. I don't know what website sells motors, but I found a website that sells motors. I found 1.15 service factor motors. I grabbed, in this case, multiple 5 horsepower, 30 horsepower, 40, 20, 15 horsepower, 25, 100, 30. So I just went through, I did how many? I did 37. 37 motors. And I said, okay, I'm going to do 37 motors. I'm going to do this fundamental test. I am going to select the conductor based upon the 90° C column and 75° C column for each of these motors. I am going to select the overload protection for each of these motors, which is at 125%. And then I'm going to select, based on 140%, raising that value to 140%. To see if I still have a protected termination, a protected conductor, and a protected motor. And here's what I learned. Let's just look at the overload protection based on 125%. Selecting it based on 90 column and 75° C column. Every single motor is protected. Every single termination is protected. But not all of them have a larger conductor. This one, I went from a 14 to a 12. This motor, because of the full load amps came down, I could do them both with a 14, regardless of whether or not you picked it off the 75 or the 90. This 5-point, because the full load amps came down, because the voltage went up, I'm at 9.5. I did them both at a 14, so same conductor, regardless if you went off the 90 or the 75. This one is the same, this one is the same, this one's the same. Look at this. Now here's the difference. This is a 5 horsepower, again, 13.9, pretty close to 14 amps of full load amps. These are the same, this is the same, and I'm looking at this column and this column, columns H and K. H and K, that's a pistol manufacturer, H and K, Heat, Clear, and Koch. Anyway, 8 and 6, so this is a 15 horsepower motor. 34 amps of full load amps, 230 volts. I picked a number 8 and a number 6, and let's scroll over. These are, now I went up in size based on the 75 degree C column. They're still both protected. I got a yes and a yes at the 125%, and I got a yes and yes on the 140%. So I'm protecting this motor regardless of whether or not I went to the 75 or the 90. I picked two different size conductors. I picked a smaller conductor when I used the 90 degree C, a larger when I used the 75 degree C. Let's keep going down. Here's another one where I went 15 horsepower. It was 17 amps at 460. Voltage goes up, full load amps comes down. I'm at a 12 and a 10. I'm sitting there saying I can go with a 12 instead of a 10. And I'm protecting it at 125%, and I'm also protecting it at 140%. I love it. All right, so let's keep going down. This one is the same. This is a 10 and a 10. This is a 300 and a 350 MCM. So this is a 100 horsepower motor. So now we got a 100 horsepower motor. Now we got 224 amps of full load current, 230 volts, 1.15 service factor. My full load amps based on the table is 248. The 1.25 is 310. If I can put a 300 MCM because the ampacity of the 300 MCM is 320, or I can put a 350 because the 75 degree C says it's 310 and it equals 310. 280 is the overload because that's 125%. But look at this. Regardless of whether or not you picked based upon the 75 degree C or the 90 degree C, neither overloads will protect the conductor, will protect at the 75 degree C column. What's the 75? The 75 degree C is 310 in one case, and I've got 313.6, and it's 285 in the other, and I've got 313.6. So here's my, and I found a couple of these. This one, oh, up here, these two didn't. Look at this. They were both the same conductor, and these are 40 and a 20 horsepower, a 20 horsepower and a 40 horsepower motor at two different voltages. I'm using the same conductor for both the 75 and 90 degree C, and my 140% is still not less than the 75 degree C column for the termination in the equipment. So I did, out of all these motors, I did 23 of them. Why does this say 23? Oh, 23 were okay. 14 were not okay based on the 90 degree C column. So 61% of my examples did not protect at the 140% mark. When I increased the size of the conductor based upon the 75 degree C column, gives me a larger conductor, only 6 out of 31, well, they should both add up to the same. 37, I did 37, so 6 out of 37 failed the 140%. That's only 19%. No, that's not 19. That's let me do that. I gotta do this right? So I gotta do some I gotta do the quantity U3 plus T3. That's not right. Control Z. I need U3. I need U3. Line up. I need U3 plus T3 is the total. And I got to do T3 divided by that. That's not right either. Ah, crap. Anyway, I'm undo, Control Z, Control Z. Anyway, I only had 6. I only had 6 out of 6 out of 37. 6 out of 37 failed when I selected the conductor based on the 75 degree C. 14 out of 37 failed the 140%. So, bottom line, my takeaway is selecting your conductor based on 75 degrees C gives you a better chance of being able to adjust that overload. It doesn't matter if you're at 125%, at least for all of these that I did. And I did a wide variety of motors. So I think there's a lesson there, but I think the code language can use a little help to match what we do. We already select the conductor for motor circuits based on the 75 degree C column. I don't want to change that. I didn't go there when I read the language. But, all right. Ooh, here we go. Never seen failure in the middle. The terminations, oh, you know what? My volume is off. The terminations are the weakest point, yep. Never seen failure in the middle, I agree. It's always at the terminations until someone gets into it with a shovel. That's true, that's true. Would overload class make any difference here on the 100 horsepower motor example? Overload class. On the 100 horsepower example. I don't know, Alan. Give me an example. When I think of an overload, here's what I think. An overload has a pickup point, right? And let me draw it. Here's what I'm thinking, Alan. That is a really good question, and I hope. Let me see if I can close some of my apps. And me and iPad, do we get along? Me and iPad are not getting along right now, and I think it's because I got the wrong cord. Woo! Got a long beep. Yep, there we go. Okay, had the wrong cord. So, Alan, when I think of overload class, your overload is going to look something like that. Isn't that beautiful? And it's yellow, like Bussman yellow. So here's what I think, and I'm testing my knowledge here so I can use your help. If I look at 600%, remember this would be the overload rating, and then I'd have a 600%. I believe that the overload class tells you what the shape of the curve looks like, so it won't pick up at a higher, or if I say that this overload is, let's look at the example for the motor. You said 100 horsepower motor. If I said that if I said I needed an overload at 280 amps, no. Yeah, 280 amps. My class of overloads is a 280 amp trip will always be a 280 amp trip. It's just that it'll trip faster or slower at 600%. I think that's what that means. I'm almost positive that is what that means. Let me look. Trip curve for class of overloads. And I'm going to just look and see what I get. Images. I don't want to do that. Oh, here we go. Yes. All right. Yes, it's what. Okay, perfect. Wait, I don't know who put this out. C3 controls. Cam A left. Here we go. There it is. This is what I'm looking for. All right, so your class of overload doesn't change the pickup point. It doesn't change the pickup point. It changes the slope. And it's at 600%. So in this one here, 600% would be about right here, because this is 100%, this is 200%, and this is 600%. So if each class takes so many seconds at the 600% mark, then what you're doing is you're changing the slope of the overload. And what that does, in my opinion, let's go back to this. Me and iPad, we get along sometimes. What that does, Alan, is, let me draw another TCC curve. I'm starting to like the yellow. Do you guys like the yellow? All right, so this is time, and this is current. And the motor start curve would look a little bit like this. There's my full load amps. There's my transition. Oh, there's my transition. I just like to do the. And then I have my locked rotor. And then down here, I do something like that, which is the asymmetrical nature of the start curve. And then, if I think about a motor circuit protector, which motor circuit protector, let's talk about that real quick. Motor circuit protector is there for short circuit protection only. And what table 430.52 C1, remember this is rating or setting of individual motor circuit. For individual motor circuit, this is in motor, branch circuit, short circuit, and ground fault protection. So this is your rating or setting for an individual motor circuit. Protective device that has a rating or setting not exceeding the value calculated in accordance with the table given in 430, this table here, shall be used unless otherwise permitted in A or B. We're going to go with this for now. If I have an instantaneous trip-only breaker, I'm using this puppy right here. And if I am in a polyphase motor other than wound rotor, I can go up to 800 amps. All right? So if I can go up to 800 times, that's 8 times the value. So 800%. Bump, 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 bump. Me and iPad. So I could have, say, an instantaneous trip breaker, which means there's no overload. So I come straight down, and I come straight down, and then I come over, and I hash this puppy. All right? So there's my instantaneous only. Instantaneous only. I call that a motor circuit protector. And if I wanted to do the Eaton thing, boom, I go to Eaton, E-A-T-O-N, motor circuit protector, time current characteristic curve, TCC, E-series motor circuit protector, ba-da-bum-bum-bum-bum-bum. It looks like a breaker, smells like a breaker, probably tastes like one. Lick the next one you see, let me know what it tastes like. If you go to the time current characteristic curve, which is where, there we go. I'll show you what they look like. That's not what I wanted. That's a CJ. That's not what I want. Is this the right one? HMCP. Eaton Series C motors, HMCP, magnetic only type breakers. Well, when I come down here, spec, CJ frame, CG frame. Let's try the G frame. And the reason I'm like, this doesn't make sense is because I'm looking at an overload. These are all standard breakers. Where is the... That's just the Series C. That's the GHB. That's not a motor circuit protector. We got the wrong link. All right, so here's what I'm going to do. I'm going to go eaton.com/TCC, time current characteristic curve. And I'm going to do special application, molded case circuit breakers, motor circuit protectors. There we go. I think we have the wrong link. Series C, motor circuit protectors. Yeah, here we go. This is what I'm looking for. All right. You'll see it's just a straight line up. There's no trip curve. And then they have the range, right? So range setting 15 to 30, 35 to 70, 300 to 600. So you can adjust that. And you'll see how down here we curve over, and there's your instantaneous on that breaker, and boom, it's just a straight line up. There's no overload on these. It's just a straight line up. Here's another good one here. This one actually shows the band. So A, instantaneous pickup setting, if you turn the rotary dial to A on this model number breaker, on this model number, A is 350, B is 400, C is 440, and so forth and so forth. So if I go back to this, that tells me I can move this curve left and right based upon those dials that are on the device. And I can go, based upon the code, I can go up to 800% of the full load current, right? 800% of the full load current. Okay. And then, so now the overload, and all of this for this freaking overload, the overload would look a little bit like, let's say that I took that out, and let's say that I put an overload like this. Okay, so this is my overload. And the class 10 versus 20 versus 30 would do this for me. And I'm just, you can tell I'm swagging it. I have SKM, but I'm not bringing SKM for this. That would take way more time than it's worth. You get the point. So, Alan, what I think is that your class 10, 20, oh yeah, you got it right there. Class 10, yeah, class 10, so it's about trip time. Yep. So in my opinion, you're closing the distance between the knee of that start curve and the overload. So by going to a class 10, I'm providing better protection for my motor. I don't have a code requirement, to my knowledge, around class overloads. Wrong computer. I'm just going to look for class in Article 430. They got classified locations, classified classifications. Oh, here we go. Oh, bada bing, bada boom. Here's where it's at, Alan. In 430.22, conductors that supply, in the small conductors, 18 and 16, Whoop, it's 18 and 16. Here's where we got it, Alan. It says conductors for small motors shall not be smaller than a 14 gauge. And remember, I went to 14, so I set in my spreadsheet the limit. I said, don't go less than 14. But it says you're permitted to go smaller than 14 in these two conditions. You can go to an 18 gauge copper, individual copper conductors installed in a cabinet enclosure, jacketed, blah, blah. Oh, there's some more blah, blah, blahs. And then it says the circuit supplies a motor with full load current rating as determined by A1 of greater than 3.5 amps and less than or equal to 5. So it gives you a range in the full load amps. And the circuit is protected in accordance with 43052. And the circuit is provided with a maximum class 10 or 10A overload protection. So what they're doing is they're telling you that you need to make sure your overload responds fast on these small conductors. You still have the same pickup point, right? But because it says 430.52, and 430.52 is going to tell you the rating or setting, which is dual element, there's your overcurrent short circuit protection and all that jazz. And there's your overload relay table. We're going to get into 430.52 here shortly. But they give you specific requirements. So very good. And you know what? You're like a walking code book and an engineer. You're one of the engineers. So yes. So and then the class 20. The class 20 is required when you're at the circuit supplies a motor with a full load current rating as determined in 3.5 amps or less. So that's for an 18. 16 it has the same thing, a class 10 and a class 20. So perfect. So when it comes to conductor selection, man, that was a really good adventure, in my opinion. When it comes to conductor selection, I think if I'm on an exam, you got to be careful if you're on an exam. You've got to know, in my opinion, everybody teaches at 75 degrees C. So if I'm doing an exam, I'm going to pick 75 degrees C. If I was engineering an actual installation, now I would probably use the language and go off the 90 degrees C. And if I had an electrical inspector flag it, I would try to work with the inspector and say, help me understand what I'm doing wrong. I'm protecting the termination at its 75 degrees C rating. I'm protecting the conductor at its ampacity. Help me understand what I am doing incorrectly. That's sort of just where I'm at. I don't know. And it might be completely wrong. I'm just saying that's where my head's at. And I think I have research to back up my argument, but that doesn't mean I'm going to win my argument on a job site. All right, so 430.22 speaks to the motors. Now, there is this E. There is a section E, other than continuous duty. It says conductors for a motor used in a short time. Yes, Laurel, research is in the house. Thank you for showing up, Laurel. 430.22G 1 and 2. That's your 18 and 16 gauge. Perfect. She's probably still watching. There's probably a time delay. So here's my next adventure for the conductor selection is other than continuous duty. It says conductors for a motor used in a short time, intermittent, periodic, or varying duty application have to have an ampacity not less than the percentage of the motor. Steve. I got to quit watching chats. I'm going to get to chats. E says percentage of the motor nameplate current rating shown in 430.22E. So we have a table. And this is for, remember the other table that we looked at don't know how to do this. Oh, there we go. The other table that we looked at was continuous duty applications. This is a non-continuous, this is intermittent use. I would give a good example of this might be like a little sump pump that just turns on every now and then. It's not running all the time, as if you don't have a water problem. But it doesn't run all the time. So if I looked at table 430.22e, what it tells me is I have a 5-minute rated motor, a 15-minute rated motor, a 30 or 60-minute rated motor, and then you have a continuous rated motor. And you'd say, well, wait a second. If I have a continuous rated motor, that's covered up above. And I would technically agree with you. I'm not sure why that column is there, actually. Conductors for a motor used in a short time, intermittent, periodic, or varying duty application. I think this is a non-continuous rated motor. That's what I think. I think this is a non-continuous rated motor because, and the reason I say that, up here, it says conductors that supply single motors used in continuous duty applications, and I have a continuous duty motor. This is a non-continuous duty, so I would say I would argue this is a motor that is not rated for continuous duty. Then it tells me that if I'm going to use that motor in a continuous, it says a continuous rated motor. I mean, if I have a continuous rated motor, then it's a continuous duty motor. Help me. Help me. What do we mean? What is? I don't understand that column. That does not, it does not compute. If that motor is a continuous duty motor, is a continuous rated motor equal to a continuous duty motor? So, Alan, I need you, buddy. What's the difference between a continuous rated motor and a continuous duty motor? I'm going to have to open up MG1. A continuous duty motor is designed to operate continuously or nearly continuously at its rated power without overheating. In contrast, a continuous rated motor is a broader term referring to the continuous power or torque that a motor can output. There is a difference. Wow. Let's go to Article 100 and see if it's a defined term. Open a new tab. Wow. Let's go to continuous. Concealed, conduit, continuous load. There's no continuous duty. It works at rated all the time. I think that's what he meant. Rated versus duty. Yes, Robert. Yes. It's rated versus duty. A motor can be rated for continuous duty, but could also refer to the peak continuous torque. Let me find, you know what, you're going to make me open MG1. All right, I hope I have a copy of MG1. NEMA documents, MG2, MG3. Where is MG1? There's MG1. All right. And my folder is empty. I have MG1. There it is. MG1 2021. It was an older version. Okay. This document is 648. All right. I I think that NEMA reference gives the tripping curves for the 4 common motor classes. Motor class. Oh, let's see if, I know there's a difference for inverter duty. Let's look at duty. Well, let's go back to chapter 4, continuous rated. I'm going to search MG1 for continuous rated. Overload. The generators, that's a generator. Continuous rated, 100% load. Observable temperature rise under rated load conditions. That's temperature rise tests. That's a continuous rated load. Let me search for duty. Continuous duty. Not duty, duty. Rated continuous duty. General purpose alternating current motor. A general purpose alternating current motor is an induction motor rated 500 horsepower or less that incorporates all the following: open or closed construction, rated continuous duty. Service factor in accordance with 12.51, Class A or higher rated insulation system with a temperature rise not exceeding that specified in 12.42. I have got 18 hits on continuous duty. I have no hits on continuous rating. A continuous rated motor. Induction machines covered by this Part 20 shall be rated a continuous duty basis unless otherwise. Watch, if I change duty to continuous rated, and these are the one, this is a temperature, it just says a continuous rated load. Observable temperature rise under rated load conditions. Oh, you know what they're talking about. It's not, forget it. Okay, I had an aha moment, Alan. We're talking about the load that the motor is turning. It's a torque thing. I believe that is a torque thing. That's what the continuous rated load is. It's the load on the motor. It's the shaft of the motor. That's what that is. Continuous load. It's 100% load, and then they have to turn that and make sure that you don't get heat higher in that motor because you're working that motor harder at torque. Now I get it. It's about the load on the motor. Okay. Wow, continuous load. I don't have any matches on continuous. Oh yeah, continuous load. When a motor marked thermally protected is running at the maximum continuous load that it can carry without causing the protector to open. That is not the load of the motor electrically. It is based upon what you're turning. Ah, beautiful. Okay, so that sheds a different light on this table for me. I don't know about you, but for me. So continuous rated motor, meaning what the load that I'm driving, whether it be a conveyor belt, whatever it is. If it's continuous rated, then I'm sizing the conductors at 140% or up to 200% for varying duty, 140% for periodic duty rolls or coal handling machines, 140% for intermittent duty freight and passenger elevators, tool heads, pumps, drawbridges, turntables. And that makes sense. Think about it. An elevator, you're going to lift the load and you're going to be at torque. You're going to be lifting a weight and for a period of time, right? So, and if I have a coal handling machine, I've got to, whether it be, I wonder if that's like a conveyor belt, a coal handling machine. So, but in any case, it's the load on the shaft that they're talking about. And this table tells you how to size the conductors differently. Remember, up above, I was at 125%. So now what they're telling you is you can size the conductors even smaller on these, because if you're only going to run it for 5 minutes at a time, you can go down to 85% of the full load or the nameplate. Now they're using nameplate current ratings. You can go to 85% because you're only going to use that motor 5 minutes at a time. 15 minutes, you're still at 85%. 30 to 60 minutes, now you're increasing the conductor size, you're up to 90%. And if it's a continuous rated application, continuous rated, what bugs me is the continuous rated motor. I got 4 hits on continuous load. The 747 is cruising now, way over my head. Oh man, so sorry, David. What I'm trying to understand, David, is this table. When we say continuous rated motor, I believe that the motor is going to tell you it's rated for it's not continuous duty. It's rated to drive the continuous load that you can put on the shaft. The maximum load you can put on the shaft. That's my gut. That's where my gut's going. An alternative, these items shall be permitted to be replaced by a single item reading temperature rise for rated continuous load. So there is a continuous load aspect. Wow. I'm going to do some more homework on that one. There's not much in MG1 on continuous load. All right, so this, again, I'm going to use this table to size my conductors for the application. It says, note, any motor application shall be considered as continuous duty Hold on. It says, note, any motor application shall be considered as continuous duty unless the nature of the apparatus it drives, which is the shaft, and whatever's on that shaft. When I say drives, it's going to be a pump, it's going to be a conveyor belt, it's going to be something I'm driving, is such that the motor will not operate continuously with load under any condition of use. I don't know about you, but this is more confusing. The code should not be, in my opinion, this difficult. I don't know. That's just my gut. But I'm having a the enhanced content says most motor applications are continuous duty. I get that. For motors that are not continuous duty, so this is a motor that is not continuous duty, the motor nameplate currents are used to determine. So this is a motor that is not continuous duty. And if that's the case, how can I have a motor that's not continuous duty that is a continuous rated motor? There's a definition for continuous duty, intermittent duty. There's no definition for a continuous rated motor. So if I have a non-continuous duty rated motor and it's driving a load continuously, then I size the conductors larger. But I would say, is that a misapplication of that motor? Laurel, I like it. The more you know, the harder it is to do your job. You're exactly right. I just had this same discussion with somebody on the phone earlier. They're like, you get to a level of, you start to question, you're like, wait a second, what the heck does that mean? What's a how do I purchase a continuous rated motor? I don't make motors, so This is a discussion of a guy who does not make motors, who just applies motors. And oh, Alan, I know there is a difference in an inverter duty motor and inverter rated motors. Inverter duty motors are designed to be used on drives. Absolutely. Yep. Is trying to sell for drive applications, but what was not special built for pulse width modulated caused harmonics. Yes. And Robert is saying continuous rating refers to temperature limitation of the load. I wish we had a defined term. I wish there was a definition. Because what the enhanced content is saying that this table, it says for motors that are not continuous duty, the motor nameplate currents are used to determine the branch circuit ampacity. Branch circuit conductors for a motor with a rated horsepower used for 5-minute short-time duty service are permitted to be sized smaller than for the same motor with a 60-minute rated due to the cooling intervals between operating periods. Nothing in here says what that cooling period is. Oh, man. Wow. There's varying duty, periodic duty roles, intermittent duty freight. I understand all of those. And I understand that elevator is going to stop and then it's going to come down, which the motor's still working, I think. It's got to be working, still working. As long as it's not hydraulic. Raising or lowering rolls, that's your short time duty. Anyway, wow. They give you some permission if you aren't running that motor continuously. Robert, Laurel, this is not rocket science, but it's not easy either. I've got to do some homework on a continuous rated motor. Continuous rated motor, and I want to buy one. I'm going to go shopping and see if there's a continuous rated motor. Rural King Electric Motors. I'm looking for a ball door. Continuous rated motor. Here we go. There's a nameplate. What's the nameplate say? This is a 10 horsepower motor. I'll bet you it says continuous duty. Class F, nominal efficiency. Yeah, continuous duty. So there's no cooling. It works all the time. Here's the chat got definition. ChatGPT. There's no cooling. It works all the time. I didn't try ChatGPT. I should have tried ChatGPT. Continuous duty. I get continuous duty. Continuous rating has to do with the load. I agree with you. Continuous rating has to do with the load put on the shaft and the temperature because of the load. I agree with you. I agree with you. I agree with you, Robert. So I'm not sure if I like the enhanced content on NFPA link. It's probably right, but anyway, let's move on. Let's move on. I'm going to come back to that one. I'm going to do some more homework. We already talked about the small conductors, the 18, so that's the G. So then you have the wound rotor motors. You have the wound rotor. I can never say wound rotor motor. I just said it really good. So say that fast. Continuous duty, the conductors connecting the secondary of a wound rotor AC motor's controller shall have an ampacity not less than 125%. So you have the same issue when you say ampacity. Do you use the 90? Do you use the 675? Other than continuous duty, these conductors shall have an ampacity in percent of full load secondary current not less than is specified in 430.22e. And this is your light start duty, heavy start duty, extra heavy start duty, and they give you different percentages in table 430.23 Charlie. That's your secondary conductors. I didn't, Steve, I don't see a link. Where's the link? Put it up there again, Steve. I don't see a link in the chat. Send it again. Do me a flavor. Do me a solid there. So 430.23 gives you selecting of the conductors for a wound rotor secondary. And then you have, okay, now several motors. This one, this is another good one. So this one talks about when you have several motors or a motor and other loads. They tell you how to handle it. So that means I have a, let's do this. This would mean that I have say I have some lights. So now I have a conductor that I have to size, and it just doesn't have a motor, it has other stuff. Right? So now I've got to size that conductor based upon this stuff, all of these different components. So what 430.24 tells us is that the conductors that supply several motors or motors and other loads shall have an ampacity not less than the sum of each of the following. So I have to do the sum of 125% of the full load amps of the full load current rating of the highest rated motor of we'll say biggest horsepower. 2 is sum of the full load current ratings of all other motors. Sum FLC of all other motors. 3, 100% of the non-continuous non-motor load. 100% of non-continuous non-motor load. And 4, 125% of the continuous non-motor load. So if this light was continuous and this light was non-continuous, I would do 125% of that, and I would do 100% of that. One of these motors, I do the full load current, and then this motor, I do 1.25 times the full load current. So to size, and then once I get that number, it says the ampacity can't be less than that number. I add them all together. I don't see the link. And you know what? Sometimes, hold on, Steve. Let me do this. Let me go up. It could be that I have to say yay or nay, and I might have to be, let me go to YouTube Studio. I might have to give it approval, so hold on. Let me show you something. Let's go to live, and let's go to the studio. There it is. And then Stevie baby. I'm not seeing, I don't even see that I can I sent the link above. Steve, I don't see anything where I can even approve it. Oh wait, there's a plus. Engage with your audience. Start a Q&A, start a poll, members only. Ooh, I can turn this on to a members only live stream. No, I'm not seeing it. I'm not seeing it. I am not seeing it. Sorry, Steve. I got top chat. Well, let me look at top chat, live chat. No. And I don't have a setting. I'm not pop out chat, send feedback, participants, community. I'm not restricting anything. So I believe it answers the question on where you get the trip time by class. Well, Steve, email it to me. I think you have my email or my text. You can text to me too. If you send me the link, I will bring it on up. All right, so determine the conductor size. I'm going to take 125% of the full load current of the largest H horsepower motor. And if they're both equal, I just take the 125% of one of them, add the other one. 100% of the non-continuous non-motor loads, 125% of the continuous non-motor loads. I select my conductor ampacity, which I would highly recommend you use the 65 degree C column or a 75 degree C column. Don't use the 90, use the 75. And then the overload protection is going to be maximum of 125%. You are always going to protect that conductor. Excellent. All right. Welcome to live chat. Don't use the biggest horsepower. A smaller horsepower may have higher current. Ooh! Very good. Wow, you are a rock star. Do you see what he just said? Look at what Robert from Omaha just said. He said, don't use the biggest horsepower. A smaller horsepower may have higher current, 430 to 247, 250, depending upon voltage. He is right. You're right. Now, I'm assuming all of these are on the same voltage. Here we go. Accept all. Beautiful. Thank you, Steve. Cam A, monitor right. There she blows. So Steve just sent this link. I am going to, Steve, see if I can put this link, Control C, in the Chaturuno Boxerunos and see if it rejects me. See, and let me put it in. So I just added this, this link. It says overload relays typically operate on an inverse time curve. We said that. They are rated by trip class. Yep, trip class specifies the length of time it will take for the relay to open in an overload condition. In Europe, the shape of the overload relays trip curves are defined by ANSI IEEE, a few examples. And then you have, in North America, we have 5, 10, 20, and 30, class 5, 10, 20, and 30 overload relays. Will trip in 5, 10, 20, and 30 seconds, respectively, at 600%. I knew 600% was in there. 5, 10, there you go. And it tells you. So, again, it changes the slope of the thermal overload. So, that's a good thing. I'm liking this. So, oh, and so, Robert, so it's the 125% of the largest motor, highest rated motor. 120% of highest rated motor. And then the full load current of all other motors. Very good. Very good, Robert. Man, you're a rock star. Okay, so. All right, so let's do this. Me, camera A. I know I got a lot of light here. I am. All right, I think. Okay, so we went over, I think, the ampacity. So then we have multimotor and combination load equipment. The ampacity of conductors supplying a multimotor and combination load equipment shall not be less than the minimum circuit ampacity marked on the equipment. So I like this. Success. I get a gold star today. Yes, put that right on your forehead. Right up there. I wish I could do that. Full load current not rating. Yes. Hold on. Full load current rating. Full load current rating. Highest FLC rated motor. There it is. Man. It must be Friday. All right. 125% of the full load current. FLC not rating of motor. It's 125% of the highest full load current. Oh, no. That's right. I had that wrong. 120% of... Oh, man. 125% times the full load current of the highest rated motor. That's the way it's written in the code. It says 125% of the full load current rating of the highest rated motor. So that's what it says. And that's what I'm going for. All right. And then there are some exceptions. We got the, what do you call it? Yes, Robert, that would be, when we say full load current, that'll be the tables. Unless it says nameplate, right? So this says, it doesn't say of the nameplate, so it would be out of the tables. I agree with you. The ampacity of the conductor supplying motor-rated fixed electric space heating. Oh boy. There's 3 exceptions. Read the exceptions. And then you have the 430.25. This is where you get on a lot of that HVAC equipment. On the HVAC, thank you, Robert. On the HVAC equipment, you have multi-motor and combination load equipment. I got the nice job. The ampacity of the conductor supplying the multi-motor and combination load equipment shall not be less than the minimum circuit ampacity marked on the equipment in accordance with 430.7D. Where the equipment is not factory wired and the individual nameplates are visible, in accordance with 430.7D2, 7D2, the conductor ampacity shall be determined in accordance with 430.24, which is what we just did. So if you have the minimum circuit, this is a problem I have between Article 430 and HVAC equipment. If I go to 445, is it 440? 440? I'm getting tired, guys. 440. 430 is motors. 445 is generators. I think it's 440 for HVAC. Yeah. 440 for air conditioning and refrigeration equipment. So I like the way 430.25 is written. So if I go to 440 for air conditioning equipment, and I go to 440.6, why am I not seeing 440.6? NFPA link is giving me, there it is, 440.6. Where's the minimum circuit ampacity? There it is. That's in 440.35. So 440.35 has similar language. 440.35 says the ampacity of the conductor supplying multi-motor and combination load equipment shall not be less than the minimum circuit ampacity marked on the equipment in accordance with 440.4b. So I can have air conditioning equipment that has that combination load or the multi-motor and combination load equipment, and in 430 I can have the same thing. 430 in 430.20 430.27 27 no 25 430.25 is when I have a motor, a multi-motor that would not be, I guess, listed as air conditioning, right? Because if it's listed as air conditioning, David, I would go to 440. If it's not, then I would go to 430. And you're right, Robert, 440 is completely separate from 430. And then 440, I'm going to have listed equipment. 430 is dealing when I'm making my own motor circuit, or I may buy a piece of equipment that is not air conditioning equipment. That could be a piece of industrial controls equipment that has been assembled by a manufacturer. Oh man, then you're going to throw 595 into this picture. And then, that's really muddying the waters. But you're right, we bounce around a little bit. But the key message, I think, is that when I'm in 430, I've got to determine when I go to 430, when I go to 440. To David's point, when I go to 595, I need to make sure that I'm having the right equipment. And Steve, I just saw your comment. You are absolutely right. It's not easy. It's if we're going to have a discussion about what a continuous duty is versus what continuous rating is, and we're going to go through all these debates, and I read this language and we go, well, what is it? What does that mean? And we've got some smart individuals on this stream. Imagine a person coming out of high school, going into the trades, coming out of college, going in, becoming a new engineer. In college, they don't teach you this stuff. They don't teach you this stuff in college. I don't care what university you go to. And then we have to try to understand it. And that's the value and importance and significance of understanding and writing language that is clear and concise. And then Robert says, yes, if it was easy, everyone would do it. We are professionals, and we still don't do it right sometimes. I don't, I don't buy the, I don't buy the statement that you need to be a qualified person and you have to go through training. You should not have to go through training to understand these words. I think the training could be the way you have to bounce around the code. But if I read a sentence and it says ampacity, I go to the defined term ampacity. I know exactly what ampacity is. when I deal with protection, if I want to protect the conductor at its ampacity, I need to be able to tell you how to do that. If I want to protect the termination at its current rating, I need to know how to do that. If I want to understand temperature ratings, I should go to 110.14. It should not be difficult to understand, but unfortunately, it is. So, all right. Well, I try, Robert. And I try to do a good job, and sometimes I'm right, sometimes I'm wrong. Just like my cousin Vinny. Win some, lose some. So, Steve, a license holder can walk right into a manufacturing facility, even though all his experience may be dwellings. This is where people really do have to have an ethic about qualified in themselves. Yes. I'll tell people all the time, I'm a licensed professional engineer. I do power systems analysis and design. If I'm a fish out of water in motors, then I'm a fish out of water in motors. If I'm a fish out of water in selective coordination, then I shouldn't do selective coordination. If I'm a power systems engineer, you don't want me working and making a computer. Because I don't know how to make a computer. Although I have, but I mean, soldering on a motherboard. I don't know how to solder. I've tried soldering. They call me grapes. So, anyway, we went through, I think we have done about all we can with selecting the conductor. We're going to get into selecting the components next time. And I know this is like twice, we focused a little bit more on this 75 and 90 degree, and I know I've had one person complain, but that is, I apologize for being slow, but that is what I do, don't you know? You said all along, help, we're walking through it together. I am, you're right, I am. We're walking through this together. So I am walking through these language. We're reading the language, taking it for what it is, and taking notes on where I think we can improve the language, and I will be making some public inputs. I'll share all of those with all of you as I pull those together. And don't you know, now the next edition, I can't, Tara isn't up there, but NFPA link will now let you look at the 2026 National Electrical Code. If you go to, and then I'm going to close out. If you go here and you say change edition, look at this. I can click on the 2026. Look at that. I got to try to make it bigger and I can't. 2026 edition, change edition, and look. Oh. In anticipation of the proposed structural changes for the 2029 edition of the NEC, digital tagging or linking in the production of this 2026 may display shaded areas not affected by technical changes. To compare the current and prior edition text, click on the Delta icon. To view completed revision details made to the 2026 edition, refer to the first and second draft located in the archived revision. Those are for all you. I like that. That's a nice little addition, NFPA. And I believe there is an annex that I thought they were going to put an annex in to show you. There it is, Annex L. Proposed reorganization or organization of the 2029 code. Oh, look at this. Look at this. They have the article number in 2023, the article number in 2026, the article number in 2029. Does it get better than this? This informative annex? NFPA did a really good job with this. You know, they did a really good job. Look at that, Chapter 3. They're showing you where it's all going. Look how many chapters. 12, Chapter 13. Chapter 14, Chapter 15, Chapter 16. Crazy Eddie's insane. Holy cow. Look at this stuff. Chapter 18 is hazardous locations. Ba-da-ba-ba-ba. Look at that. Chapter 19 is occupancies. You have healthcare, assemblies, theaters. Do you think we need a data center occupancy? Do you think we need a data center occupancy? That's my question. All right, so go out there, check out the latest and greatest that NEC has to offer, and that's all I have to say about that. I am going to sign off. I am in my kitchen. Maggie's leg is getting better. We go to get an x-ray on the 25th, I think it is. 25th. I might have to record my my IAI News Live for next week. I don't know. Time will tell. We're going to be going live from NECA with Kyle Krieger. I'm going to be doing a Charlie Trout code question of the day discussion with Kyle out in Chicago. We'll probably, I don't know if we're going to go live tomorrow or Saturday. We'll pick the times. And it's all good. Swamped as usual, but that's okay. All right, everybody. Thank you for tuning in. Thanks for all of the dialogue. Thanks for all the help, Steve, Robert, you are the man, David Engelhart. We had, Alan Bernstein. Who else did we have? We had research. We had research here, so that's a good thing. Laurel in Omaha. I'm going to call it a day. Thanks, everybody. I learned a lot this session. I hope you did as well. See you next time. See ya.